I don't know about you, but this method of undetermined coefficients, it has a certain practical efficiency to it, but it doesn't really make me feel like I understand why the guesses we were making for particular solutions actually work. I mean, they did work in practice, but it seems like there should be some deeper meaning behind why the guesses should be what they are, especially in the case where there's overlap between the particular solution guess and the complementary solution. Why is it that you should multiply by x? So one way to sort of get a deeper understanding of what's going on is to phrase things in terms of linear operators. So let's consider solving a non-homogeneous linear differential equation like this one. We do need constant coefficients for this to make sense. So we're going to assume that all of our a coefficients, a sub n through a sub 0, are actually constants. So in this situation, we can rewrite this differential equation using our linear operator notation. So this would be a sub n times the operator d to the n plus a sub n minus 1 times d to the n minus 1, all the way down to a sub n times the operator d plus the operator a sub 0. This is all applied to y equals g of x. This left-hand side, this is a linear operator, so let's call this L. So now our equation is the operator L applied to y is g of x. Okay, now in these situations where undetermined coefficients worked, this right-hand side, g of x, had a special form. It was exponential, it was sine or cosine, it was a polynomial. And what unites those three cases is for all of those three cases, there is a finite order constant coefficient linear differential operator that kills g. When I say kills, what I mean is this linear differential operator, let's call it L sub 1, we can find some linear differential operator that if you hit g with it, it gives you 0, right? So for example, right, if g were e sub x, then the linear differential operator that kills that function, that makes it 0, is the operator d minus 1, right? Because e sub x, if you take its derivative and subtract g itself, then you get 0. Okay, so what makes undetermined coefficients work is that for the inhomogeneous term, there is some finite order constant coefficient linear differential operator that, when applied to that homogeneous term, gives you 0. So the trick here is, now that we have this extra linear differential operator, we can hit both sides of the original differential equation with it. So then we get L1L applied to y equals L1 applied to g, but remember, L1 applied to g is 0. So this turns our original differential equation, which is up here, this turns our original differential equation, which was inhomogeneous, into a higher order homogeneous differential equation. So it's higher order because, right, if L was order n and L1 was order m, well, here you have order n and order m, and so together they make order m plus n. All right, so solving a lower order inhomogeneous equation is like solving a higher order inhomogeneous equation. But why that doesn't quite, that sort of explains why only some right-hand sides will work for undetermined coefficients. It's because we have to be able to find a finite order linear differential operator that makes g 0. But it doesn't really explain why, if there's overlap between the complementary solution and the particular solution, why you have to multiply your particular solution by x. So let's look at that. So for the original differential equation, or for the associated homogeneous equation, L of y equals 0, right, that has some complementary solution. And in this case, let's suppose that just to have an example that sort of illustrates the general theme, let's say that our linear differential operator is, let's say it's just d minus 1. Okay. And again, to have a particular example that illustrates the general theme, let's say that our inhomogeneous term is e to the x. Okay, so our original equation was d minus 1 times y equals e to the x. So this is our associated homogeneous equation. This is the original equation. Okay, so to turn this inhomogeneous equation into a higher order homogeneous equation, we have to figure out some operator that kills g. So we need to find L1 so that L1g equals 0. But g is e to the x, so we know what L1 is. That's d minus 1. So then we hit both sides of this with L1. On the right-hand side, we get L1 e to the x. Or sorry, let's write it out. It's d minus 1 times e to the x, but that's 0. So the right-hand side is 0. And on the left-hand side, we started with d minus 1 times y, and we're hitting it with d minus 1 again. But d minus 1 applied to d minus 1 applied to y, that's d minus 1 squared. So because the linear differential operator from the equation overlaps with the linear differential operator that kills g, it turns our higher order differential equation into this repeated case. So if we wrote out the characteristic equation for this differential equation, it would be a repeated root case like this, and that repeated root would cause you to get a solution that's multiplied by x, right? So this would give you x e to the x instead of just e to the x. So that's sort of the deep reason why, if there's this overlap between the original equation and the linear operator in the homogeneous equation and the linear operator that kills d, that's why you end up having to multiply x until this repeat is removed. It's because you're actually getting a repeated root case. And we've seen that in a repeated root case for a homogeneous equation, you just get powers of x multiplying your initial solution.